Well, good morning. We're back with starting at chapter 2, and we're going to be talking about uh, circuits that are either parallel or in series or in combination of series and parallel circuits. So last chapter we looked at just one resistor, and now we're going to add two resistors or three resistors or four resistors, and we're going to see how the current and the voltage responds according to those situations. So figure 2-1 below shows a battery and multiple resistors arranged in parallel. And as you can see, each of the individual resistors basically get a portion of the current that goes through that circuit. The split is proportional to the value of the individual resistors. Higher resistance means less current. Lower resistance would mean more current. So the sum of these currents is the total current that we feed this circuit with, and that then they come back together and then they flow back through. So basically, all these currents here add up to the total current that flows out of this battery. We're going to see how that works. And we have this law. It's called Kirchhoff's current law, or we basically refer to it as KCL. And KCL states that the sum of the currents into a point equals the sum of the currents out of the point, which basically says we can't lose current in a wire. So the wire does not let current jump out of it. And that's basically all this is. So in a case like this situation right here, the total current is equal to the sum of 1, 2, 3, 4, 5 currents. We could call these I1, I2, I3, I4, I5, and I6. And you could see that I1 would equal the sum of these all together. And you could write that down if you wanted to in a mathematical equation. Okay, so here's some more figures. Down here's this is figure A. So this one would be what? I1 is equal to I2. The current into that point is equal to the current out of that point. So you'd write the equation I1 equals I2. So what do we have here? We have story problems, don't we? This is a way of writing story problems, and this is an example of, from algebraic days, we would say, okay, this is the car goes into and the car comes out, and it's got to be the same thing. Here, they split. Some of it goes this way, and some of it goes this way, which we would then write as what? I1 is equal to I2 plus I3. Here, we've got 2 going in and 2 going out. So we would write here I1 plus I2, current going into that point, is equal to I3 plus I4, the current going out of that point. So you could summarize the sum of the currents. This is the summation of the sum of the currents into a point equals the sum of the currents out of the point. Now this is a crucial law in circuit analysis. It's simple in concept and problems are easy. It's intuitive, but it does have a lot of profound effects on how we solve problems. So anytime you have a circuit, you can also always write this flow in and out of a point. Here's an example with numbers. If you go back to figure 2-3A, or excuse me, this figure right down here, if I have 7 amps in and 3 amps out, and what's this? Obviously it's 4, right? 7 equals 3 plus I. That's not a 1, that's an I. Therefore I is equal to 4 amps. Okay. In this case, we can say 4 in and 9 out. Well, what is this out right here? Well, this has got to be a -5. In other words, the current isn't flowing out, it's flowing in. So you get 5 from this one and 4 from that one. They contribute and they give you 9. Therefore, things do have signs. In other words, if I say that I is going in the left or right direction and a minus sign, it really is going in the opposite direction. So that's what that is. So you can't have minus signs. There's another important law. Kirchhoff seemed to be a big gun in this, and he was, but basically he has two laws, Kirchhoff's current law and Kirchhoff's voltage law. KCL was unknown currents, Kirchhoff's voltage law is unknown voltages. KCL, current law, KVL, voltage law. Guy's name is Kirchhoff. Okay, so the voltage law, the voltage state, the law states that the sum of the voltages around a closed path equals 0. This law says that to start at any point in a circuit, walk around in a clockwise or counterclockwise direction and write the voltages at each voltage source or load, and the sum is going to equal 0. A number of examples will give us a better understanding of this law. Now the question is, why is this law so important? It is important and it leads to a number of equations with unknown voltages in a circuit. It is useful to apply the voltage divider formula, for example, in a few pages. So we use this law again and again and again. We just don't usually say KVL or KCL, but we may. Okay, the first example of Kirchhoff's voltage law. I have a battery and I have a load. So as you walk around this circuit, what can you say? Okay, if you walk around it from some of the voltage around any closed loop have to add to 0. So as you're walking around it, you walk into the battery from the minus side, you're at a minus sign. If you walk around it from the plus side, you do plus. Okay, so when you're walking around that loop, you start at the minus side of V1, so you're at a minus, and you come around to the plus side of V2, so you're at a plus, and you sum to equal to 0. So basically you say plus 2 minus V1, and then you write equals 0. So you start at a point, here you started at A, plus V2, march around to this side, minus V1, and sums to 0. Or we could say V2 equals V1. That's easy. Okay, another way of picturing this is going up and down a ladder. I go up so many steps, and then I come back down. I come back to the same point I started at. I have to come back down the same number of steps. So the source, the voltage source, the battery, is the man going up the steps on the left. The resistance is the load, and that's the number of steps that have to come back down on the right. So one way to write this is the number of steps up equals the number of steps back down. Here is a circuit with two resistances. You've got a source, V1, and you have a V2 and a V3. So how would you write this? Start here at A, march around plus V2 plus V3 minus V1 is equal to 0. Or I can move the V1 to the other side and get V1 equals V2 plus V3. That's going up the ladder, coming back down the ladder. The one on the right, I have two sources and two voltages. In that case, I can write V3 plus V4 minus V2 minus V1 is equal to 0. Or the source voltage is equal to the load voltage. Either way. So this law says the sum of the voltages around any closed loop add to 0. How to use KVL and KCL will be the subject of problems throughout this chapter and the next. Here's an example. We've got plenty of examples in this chapter and the next chapter. So here I have a voltage across this resistor and another voltage across this resistor, but I don't know what the voltage is across the battery. but I can find it by summing the voltages around a closed loop. This is a closed loop. What is it? Well, I can write 3 plus 4, because I'm coming around from the plus side, minus V, because I'm coming in from the minus side, equals 0. The voltage source across it is equal to 7 volts. Here, I have, how many closed loops do I have? Well, I have this loop, I have this loop, and I have this loop. I have 3 loops here if I want to, but I'm going to find out here what the questions that they want to have asked are. So basically, they ask, find the unknown voltages of this. Okay, first of all, I want to find the unknown voltages of this one. Sorry about that. Here, I come around from A, plus 3 plus V minus 12 equals 0. 3 plus V minus 12 equals 0. V equals 9. Here, I look at it and I've got a closed loop with one unknown voltage. Find V1. Then I can also go the same loop and find V2. Or I can, once I found this voltage, I can go around this loop and find this V2 based on the knowledge of what I found from here. So you can either use this loop and then this loop, or this loop and then this loop. Either way works. So let's see what they did. So here, 3 plus V1 equals 12. That's one loop. I have to come back down here and find this again. V1 equals 9 volts. So now we know 9 volts right here. So now we can either go around this loop or we can go around this loop again. By the way, looking at this loop, what does V2 have to be? Has to be 6, doesn't it? Because 12, you go up the ladder 12 steps, this is coming down the ladder 6 steps, that's got to come down the other 6 steps. So you've got a couple of ways of finding V2, right? Looks like I made a typo there. Yep, we got a typo in that situation right there. We've got a typo. So this should have been 6, and it says it's 5. So again, sometimes you find it right, and sometimes you get it wrong, and I'm going to have to check that and make that change so that that will get changed out. Okay, so basically, this is an error, but we'll keep on going. Okay, now, analysis of series circuits. So far, we're looking at parallel circuits. Now we're looking at series circuits. Okay, so here I have a series circuit. Now, what is a series circuit? The current is captive, isn't it? It goes around one loop. It cannot go on multiple loops. It's in series. So the resistors are in series. It's one then the next. Okay? So now if we use, what law can we use to get this, to do this? Okay? So what law do we want to use? Well, we have to know something, don't we? We have to know the current, or we have to know the voltages, or something, don't we? We have to know something. Okay? So in this case, if I were to say the current has to go through this and then go through this, I can say it can go through this and then this and give me the voltage here, or I can say it can go through one resistor and it would give me the voltage through that. So here I can say, give me what? I can find this current in this case, and that's the same current as that. So then I can find the voltage across here, and then that gives me the voltage across here. So this is a story problem in which find the current, same current as here, and then go around and find the voltage there, because I can then find the voltage across here. Okay, so let's just see what we do. So So for 2.9c, we add the values of R1 plus R2, okay? Or we can use this equation up here, which says what? Ratio of V1 over V2 is equal to R1 over R2. And that's basically based on the fact that we can find the current through here, and then we can find the current here, and that gives us the voltage across here. So basically, same current, voltage, does it go up or go down? It goes down. It would be less than 1,000 because this is bigger than this. So V equals IR, this is going to be half of that. So you should be able to see that. But basically, it's okay. So we can go through this one and we can find this current here. So that gives us the current through that one. Okay, so that gives us the voltage across there, and then we can add these two and get us the voltage across there. Okay. Now this one, D, we add the resistors, or we can say what? Find the current here, and that gives us the same current here, and we can find the voltage that way. So let's just do that. So the voltage V1 is equal to 200 millivolts, and that way we can find the ratio. So I very rarely use this law right here, but you can use it in a series circuit. The easier way to do it, in my opinion, is to say, okay, voltage, resistance, current, same current, because it's in series. Now you can find the voltage, and that way you can find it that way. Either way it works. 200 millivolts is the voltage across it. So we can find the equivalent resistance of two or more resistors in a series circuit. It's equal to the sum of the resistances of the circuit. Figure 210A shows two resistors in series between A and B. Okay, so here is an example. So what would be our equivalent resistance? 4K plus 2K is 6K, right? 6,000 ohms. Okay. What about this one right here? In general, you can say R1 plus R2 equals R. And we call it R equivalent. So this R equivalent right here is equal to R1 plus R2. In general, R equivalent is the sum of all the resistors in the string. It's called RT, or R total. Here's figure 211. Here we have R1 plus R2 plus R3. What would be the final value? RT is, if we have okay, I should have said R1 is equal to 2 ohms, R2 is equal to 3 ohms, R3 is equal to 1 ohm. It's equal to 6 ohms, isn't it? Okay. After finding R total, use the following equation to find I. I in this circuit is what? 12 divided by 6, or 2 amps. Okay, that's also the original, that's the current in the original circuit of A. So this current here is the same as this current here, because I just combined these three into this one. Then we can go back and we can find the voltage across each of those resistors. This one would be 4 volts, 6 volts, and 2 volts, and that's my 12 volts. Okay. So let's combine some resistors and find the R total. All right, so if I have a 5 and a 3, what would that be? Well, 5K plus 3K is 8K. They're in series because they're strung together. What about this one? 4K plus 2K. They're in series, so there's a 6K. Okay, now this one is a little bit more difficult, but basically it's the same circuit because why? Well, these are in series, and these are in series, so even though we don't know how to handle this yet, we can at least say, well, this is equal to an 8K, and this is equal to a 6K, so basically we can redraw this into this. So this simplifies the innards of this to something that's much more simple than this. This looks hard. This is a little bit easier, and we're going to figure out how to figure this one out in a little bit. All right, so you got a Christmas tree or a holiday tree, whatever, and you've got 100 ohms, okay, and you got 12 lights. Okay, so what's the total resistance of each light? It's 100 ohms per each, and you have 12 of them, so you have 1.2K. So what's the current going through that? Right there. 120 volts divided by 1200 ohms is 0.1 amps, or 100 milliamps. So now you can all go home and fix your parents' or somebody's Christmas tree lights, right? So now we're going to go over and we're going to work on mini paths, parallel. You have your choice type paths, okay? In this case, we're going to use Kirchhoff's voltage law. And I'm going to say, okay, when I see this, it's parallel. When I see this, it's parallel. Either way works, and there's different equations. If you just have two, then you have more than two, but I'm going to give you the general equations for both of those. So in this case, current can choose which way it wants to go. Current can choose here which way it wants to go. Either way works the same. So currents in parallel paths equal a common voltage divided by their resistor. So this is the I1, this is the I2, based on the fact that this voltage is this voltage is this voltage. They're all the same voltages. Okay, so now let's get this equation. I total is equal to I1 plus I2 plus I3 plus I4 plus I5 plus I6 plus I7, whatever. And what law is that? KCL, Kirchhoff's current law, right? So we can write that. I1 is equal to V over R1. I2 is equal to V over R2. We can write that, can't we? You bet. Now when I put this together, I can form an equation. Okay. And here I can find I2 by the mere fact that I've not been given the voltage, but I've been given the current through this one and the resistance, so that's the voltage there, so the same voltage is across here, and I can go back and I can find I2. But I'm getting down to my equation. I want an equation for how to combine parallel resistors. All right? So, what is that rule? This is called the reciprocal rule. 1 over R equivalent is equal to 1 over R1 plus 1 over R2, and if you have 3 or more, it's plus 1 over R3 plus 1 over R4 plus 1 over R5, etc., etc., etc. So basically, this is the 1 over rule. That's called the reciprocal rule. Okay? Or, if you only have 2, R1, R2 over R1 plus R2. That's the equivalent if you only have 2. This is the product over sum rule. Product over the sum is one of the equations for if you only have 2. And you say, well, I have 3, but I want to use this rule, the product over sum. So you combine the first 2, and then you combine that one with the result of those first 2 with the third one. Is that acceptable? Yes. It's acceptable. You can do that. But that's 2 steps instead of 1, and I think you want to do the reciprocal as much as you can. Product over sum or reciprocal rule, either way works. Okay, so here's an example. Here we want to find the equivalent resistance. I have two 5K resistors, and I do the product over sum. 5,000 times 5,000 over 5,000 plus 5,000. What do we note? It's 2,500. What do we note in general about parallel resistances? The equivalent resistance is less than either of these resistors. And in this case, it's exactly half. And is that an accident? No. If you have two equivalent resistors, R equivalent is exactly half. If you have three equal resistors, it's exactly a third. If you have four, it's exactly a fourth. And you got it. If you have five, it's exactly a fifth, etc., etc., etc. So this is no accident. This is exactly half of these two, if they're equivalent. If they're not equivalent, it doesn't work. Okay, so it's an easy way to spot how to, okay, so here's another one. 3K and 6K. What's the R equivalent? It's 3 times 6 over 3 plus 6. There you go. Or it's 2,000. Okay, what is this one? I want an R equivalent. 100 times 300 over 100 plus 300. Now, is the answer going to be less than or more than 100? Is it going to be greater than or less than 300? The answer is it's less than 100. Why? Because part of the current is going to go through here, part of the current is going to go through here. So your R equivalent has to be something with a greater current, lower resistance than either of these. So it has to be less than the less of the two. And again, if you look at this and you get the answer is 150, you did something wrong. And that's a tick off or a kick off or a tip off that you are messed up. If you see this is less or is greater than the lower of the two, it's got to be less than the smaller of the two. Okay. If you have more than 2, use the reciprocal rule. 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over 4 plus 1 over da da da. Keep on going. Okay, so here we have 3, don't we? And one way to do it is to combine these two into 1, and then combine those two, and then you find the 1K for the combination. That's one way of doing it. Or you can find the 1 over 2K plus 1 over 3K plus 1 over 6K equals 1 over R equivalent. Either way works. This is the one-step approach, which I really do like. Okay? Just be practiced up on this with your calculator. Make sure you can do this. Either way gives you the same answer, doesn't it? It gives you the same answer. Okay, so let's try another one here. 3K and 6K, 2K. 3 times 6 over 3 plus 6 is 2K. Here it's, then how do you find I? Well, if you had the 2K resistor and you got the voltage, 2K resistor, 12 volts, I is equal to what? 4 milliamps, right? Excuse me. It's equal to the sum of the two. 4 plus 2 is 6 milliamps. So if I find the current through here and the current through here and add them up, it would be the same as the current through the resistance. Okay. Here, the currents are opposite the resistance. Okay, again, we don't use this very much, but you can at least note that it exists. This rule we use a lot. If you have 20 bulbs and they're connected in parallel, which sometimes they are, each of them have a 10K resistance. What would be the total current? If you have 100 volts, you have 10K on each bulb, and then you have 500 ohms if you have 20 of them. So it's 10K divided by 20 is 500. And the current, 200 milliamps. Okay, so another one. What's the R equivalent here? It's 1 over 10K plus 1 over 30K plus 1 over 50K, or 5.62 K ohms. Now, a quick check. Which is the least of these? 10K. This is less than 10K. So it's probably right. All right, so now what do we do? Oh my goodness, Ted, what do you do first? Well, you combine as you can. So what is the goal here? It's to find the R total, or the R equivalent of this circuit, isn't it? So what do you see? Well, you see two in parallel, don't you? You combine them, and then you see that new R total with this one up here, and you combine that into one. So this is multi-step problems. 10 plus 10 and a 30 gives me 7.5. 7.5 and 5 give me 12.5. So the R equivalent of this whole circuit is 12.5K. You have to see that you start here and you come down through here, and that at this point it has a choice. Therefore, these are in parallel. Combine these, then add that to that one, and away you go. Okay, here's another one. Okay, now for this one, you add these together first because they're in series, and then you combine them, and then you combine this, and that gives you an R equivalent over here. Combine the series, and then combine the parallel, giving you an R equivalent. Again, that's a way to do it. So, some general rules for reducing series parallel. Look at the circuit to identify series and parallel combinations. Replace the series and parallel combinations until one equivalent resistance remains. Okay, here's more examples. How would you do this one? Well, here I would combine these two into one. That's 7.5K. Then I would add those together to 1. Then I would say that I've got a parallel combination. Use the reciprocal rule to find the results. So you have to redraw the circuit more than once, which is not a problem. Remember, series rule and parallel reciprocal rule are the product over sum. So we're going to stop now, and we will pick up next lecture with the problems from this chapter. So we're starting the problems now at the end of chapter 2, and we're going to go through these problems in order. We're going to do them all, and I just wanted to show you these problems as we go through them, but I'm going to go to a blank page, and we're going to start working on them. So you need to have the page with the problems pulled up, and then we'll work through these, and we'll then be able to just go through each of them individually. So I'm going to move over and go to the blank piece of paper, and we'll start working on these problems. Okay, so problem 2-1 is a question on the number of equipotential points, and we want to look at that, and we want to see how many equipotential points we have. Well, every time you go through a resistor, you go to a new equipotential point. So we're looking at a voltage supply, and then we come up here, and we go to a resistor. We come down here, and we go to a resistor, and then we go through two resistors, right here and right here. We go to a resistor there, and we come over here. We have two resistors. We have a resistor right here. So I can kind of do this. I can kind of say, okay, now from here up to here and all the way over to here, down to here, that's one equipotential point. From here down to here and over to here, that's another one. From here over to here, and then over to here, down to there, that's another one. Then from here down to there, and from here over, that's another one. And then here we go all the way around, all the way back, like that, that's one, and this joins it, and this joins it. Now, how many of those lines did we have? We got, that's 1, that's 2, that's 3, that's 4, and that's 5. Do we have any more? 1, 2, 3, 4, 5. So there's 5 equipotential points in that circuit. Okay, so that's number 1. Problem number 2. You have current going in and current going out. So you have 9 amps going in, and you have 2 amps going out this way. You almost look at it and tell what it is, but you can also set it up as an equation. 9 is equal to I plus 2, or I equals 7. That's A. B, we have going in, we have 3, and going out we have I, and we have 7 down here. So we can say 3 equals 7 plus I. Well, here I is equal to minus 4. So the actual current is going in that direction with 4 amps. Number 2. Number 3. This is another problem. This is just like the one above. This is the Kirchhoff's current law. Find the unknown currents. So we start, this is just drawn a little differently, but it's the same thing. We have 3 amps steaming into that corner. We come down here, we can go this way, we can go this way. So I have 3 milliamps coming down here. I have 1 going this way. I must have 2 going that way, right? And then down here, I have 2 going that way. That's my I1. And I don't know this number here, but I do know this number over here, which is 1 milliamp. And I know this number here because it's got to go around there. That's got to be 3. So this number has to be 2. So if this is 2 and this is 2, this has to be 0. And this is 1 milliamp. 1 milliamp, 1 milliamp. So there's nothing going across that bridge. So I can write I1 is equal to 2. I2 is equal to 0. I3 is equal to 2, and these are all in milliamps. I4 is equal to 3 milliamps. That's A. And B, we have a starting voltage. We go through 10 milliamps. Then we go 2 down. So that must give us 8 over here. Then we have 1 down. And that must give us 7 over here. Must give us 7 down here. Go all the way around like this, 7 milliamps. Can't go anywhere, so it's got to be that. And I4 has got to be 7, so it's going to be 7 over here. 7 1 is going to be 8. So I5 is 8 right here. And then 8 plus 2 is what? 10. So I can write I1 is equal to 8 milliamps. I2 is equal to 7 milliamps. I3 is equal to 7 milliamps. I4 is equal to 7 milliamps. I5 equal to 8 milliamps. I6 is equal to 10 milliamps. And I think we're done. Very good. Number 4. Find the unknown voltages. So for A, we start at 12, we go up the ladder with 12, and we come down 3. We come down an unknown voltage V, question mark. We come down another 4. We get back to 0. So this is 0. We climb the ladder 12. We come down 3. We come down 4 here. How many do we have to come down here in order to get 0? So it's minus 12 plus 3 plus V plus 4 equals 0. That's Kirchhoff's voltage law. What does V have to be equal? V have to equal 5, right? 5 volts. So this is 5 volts. That's A. B, we start with a voltage supply at unknown. Then we drop 8 volts here. We drop an unknown number of volts here. That's V1. We drop 4 here. And we drop 7 here. So if I can sum the voltage around any loop, it's minus V1 plus 4 plus 7 equals 0. V1 is equal to 11. So I can get 11 volts here. Here I have 8. I go around this loop. 8 and 11 has to equal what? Minus the voltage of the supply plus 8 plus 11 equals 0. The voltage of the supply is equal to 19 volts. V of the supply is equal to 19 volts. Okay, keep on going. C, I have a voltage supply, and I have another voltage supply. So I climb the ladder twice. I get part of the way up with this one. I get 6 volts up with this one. So I get 6 steps up, and then I get the rest of it I don't know, but we'll find out how to do that here. And we have 3 coming down. So I have 2, 3, and 10. So I have minus 6 minus V plus 2 plus 3 plus 10 equals 0. 15 minus 6 is 9. So voltage better be 9, right? Minus 6 minus 9 is minus 15 plus 2 plus 3 plus 5 is equal to 0. So voltage, this voltage supply here, it better be 9. That's C. D, again we have this strange looking thing called a Wheatstone bridge. Go out, come down, go across, come down like this, come down like this, come down like this, and do this. Okay, so we have 15 here, plus to minus. We have 3 here, plus to minus. We have a V2 here, plus to minus. I have a V3 here, plus to minus. I have a V1 here, plus to minus, and I have a 1 here, plus to minus. So I can look at this and I can say, okay, so I can go around this loop and get V1. I can go around this loop, kind of a strange loop, and get V3. I can go around this loop and get V2. So let's try that, okay? Minus 15 plus 3 plus V1 is equal to 0. V1 had better equal 12. So I'm going to put a 12 over there. 12 equals V1. All right, so V2, I come 15 minus 15 plus V2 plus 1 equals 0. V2 is equal to 14. So I put a 14 there. Plus 14 minus. Okay, so if I drop 14 here and 3 here, what's the difference? What's the voltage around this loop? What's V3? Well, I can do it a number of ways. I can go this convoluted loop right here, which is kind of a way of doing it. I can say minus 15 plus 3 plus V3 plus 1 equals 0. V3 better equal 11, plus to minus. Now let's check. If this works, we'd better get this little loop right here. V2, which is 14, so 14 minus 11 minus 3 equals 0. Does that happen? Yes, it does. So we know that these values agree. The 11, the 14, the 1, the 12, and the 3. So we found all the unknown voltages. If it doesn't check out, if it doesn't agree, then we know we got a problem, but it does. Okay, so find the unknown voltages and unknown currents in this circuit right here. So 2-5. I want all the unknown voltages and currents. So the first one here is a voltage, and then I have a 1K, an unknown voltage, and I have a 1K up here, and I have a V1. I don't know what V1 is, and then I have a 3K, and I know my voltage across it is 12 volts. Plus to minus is 12. So I know what my current is. My current is what? I is equal to V over R. This is a series circuit, so it's 12 divided by 3K, or 4 milliamps. So I have 4 milliamps coming around here. So 4 milliamps times 1K is what? 4 volts. 4 volts, 12 volts gives me what? 16 volts here. So now I know all my currents. The 4 milliamps is coming through this resistor, coming through this resistor. I know all my voltages, 4 volts and 12 volts, and I know my voltage supply, which is 16 volts. Okay, so that's A. B is an unknown voltage supply again, and I have a 1K, a 1K with an unknown voltage, a 2K with 6, plus 6 minus, so that tips us off to the current, and then a 3K with an unknown voltage. So I don't know this voltage, I don't know this voltage, I don't know this voltage, I just know this voltage, but I do know the current. I in this circuit is what? 6 volts divided by 2K, or 3 milliamps. So I've got 3 milliamps steaming around that circuit. So 3 milliamps times 1K is 3 volts. 3K times 3 milliamps is 9 volts. So I have 3 volts, 6 volts, and 9 volts is my supply. It's going to be 18 volts, right? So I have one current, 3 milliamps, steaming around a circuit, 3 volts across the 1K, 6 volts across the 2K, 9 volts across the 3K, 18 volts for the source. That's B. Okay, C, a little different. For C, I have a 30 volts. Oops, straight away there. So C, I have 30 volts. 30 volts dead. And I have a resistance of 4, 6, and 2K. Okay, so I have 4K, 6K, and 2K. So in series, how many K is it? So what would be my R total here? If I have a voltage supply and one resistor, what would that resistor be? You add them together, right? It's 12K, and I have 30 volts. So what's my current? I is equal to V over R. What's 30 divided by 12? It's 2.5, right? And it's in milliamps. So I have 2.5 milliamps steaming around there. Now I can go back and I can pick off my voltages. My voltage across the 4K is what? It's 10. What is 2.5 milliamps times 6K? Better be what? 15 plus or minus? What is it across the 2K? Better be 5 plus or minus, right? And does this add up to 30? Yes, it does. 5 plus 15 is 20, plus 10 is 30. You're good. That's how that one's done. Okay, so that's the unknown voltage. The unknown current is 2.5 milliamps. Find that first. You find the one that's easier to do. So that's the one that's easier to do. And D, let's go to D. In this case, I have a 9 volt, and I have a 6 volt. And over here I have a 2, 3, and a 1. $2K, $3K, and a $1K. So here I combine these two. That's equal to what? 15 volts. Over here I combine these three into what? One resistor. What is 2 plus 3 is 5 plus 1 is 6K. What's my I? Is V over R, or 6K. What's 15 divided by 6? Another 2.5, right? Popular number today. 2.5 milliamps. So I have 2.5 milliamps steaming around that corner. Okay. Now I can go back, multiply 2.5 times 2, or it's 5 volts, plus or minus. Times 3 is 7.5, right? And what about 1 is 2.5. You ought to add these three up, and you get 15, which is exactly what you do. So that gives you the answer to 2.5D. All right, now we're moving on. 2.6. So 2.6. Find R equivalent at the terminals. Okay, for all right, so for each of these circuits for 2.6, so this would be 2.6A. When we are at terminal A, we go down through a 1K, and we add that to 12K, plus we add that to 30K. That's 42, 40, it's 43K, right? So our R equivalent, or R total, R equivalent, is equal to 43K. Okay, so, and that would be for A. Now for B, you'd have to answer it for switch A open. You have an R equivalent of 100 ohms plus 50 ohms, and that's equal to 150 ohms. A closed, B open. Now we have 150, we redraw, and we have what? We have 4K, right? So what is the R equivalent of this? R equivalent of this is the parallel rule. 150 times 4,000 divided by 4150, or what? 144.57 ohms. Is that right? Well, it's less than the least of the two, which is about right. So we know it's a little bit less, and it's just a little bit because this is such a much bigger number than that, so it dropped just a little bit, but it did drop. And then we do it again for switch A closed and B closed. So now we have the 150, and we also have the 4K, and we also have another one that is what? 600K, right? 150K plus 450K is 600K. So now let's do the reciprocal rule. Would that be the best way to go? You could. You could also use this number because this is the number you found for these two, and then make it in parallel with this one, and that would be acceptable as well. Let's do it with the reciprocal rule. R equivalent is equal to 1 over 150 plus 1 over 4K plus 1 over 600K. And you got to get the zeros right. Okay, so 1 divided by 150 plus 1 divided by 4,000 equals plus 1 divided by 600,000 equals, and then you do the 1 over. Which is what? 144.54. Barely dropped from this number over here. It was 144.57, now it's 144.54. But that's what you'd expect because this is such a big number in comparison to this number. But that's how it came out. Okay. Anyway, it's good numbers. Keep on going. And C doesn't really matter. It doesn't really matter where we start from, right or left. It's from the terminal, and I'm going to redraw it based on the terminal on the left instead of the right, because I like to do it that way. It doesn't really matter. I have 100, I have a 400, and I have a 500. 100 plus 400 is 500, plus 500 is 1,000, or 1K. So the resistance from here to here is 1K, which is the same as drawing it the other way. It's the same thing. So we're down to 7. Now we have parallel circuits. This is our parallel question. So we're going to do 2.7. And the first one is A. So for A, I really don't know the voltage. They don't tell you that, do they? Dirty bums. And then this is an unknown voltage, but I have the resistance 10K. Over here I have 30K, and I have 1 milliamp. You got to tell you enough to start, okay? So I know the voltage down through here, it's what? 30 volts, right? So it's 30 volts plus to minus here, 30 volts plus to minus here, because somewhere around any closed loop has to be 0, 30 volts here. So basically now I know what the current is here, which is what? The current down for this row is 30 divided by 10, or 3 milliamps. I have 10 milliamps here, 3 milliamps here. What's going back here? 4 milliamps, right? So I have 3 milliamps coming down through here, 1 milliamp coming down through here, and I have 4 milliamps total. Away I go. That is A. Now B, I have, again, it may not be pretty, but let's draw it here. I have 2K and an unknown voltage, or an unknown current. I have 3K, and I have a known current of 4 milliamps. And I have 30K and an unknown current I. So I need to know the voltage across here, and then I can find the voltage across here and across here, and and then I know the voltage across here, right? So 4 milliamps, 3K is 12 volts. Plus 12 minus. Plus 12 minus here, plus 12 minus here. So I have 30K and 12 volts. That gives me what? That's 0.4 milliamps coming around here. And I have 2K and 12 volts, so that's 6 milliamps. So I have 6 milliamps coming down here, 4 milliamps coming down here, 0.4 coming through here. So what is the total? 6 milliamps plus 4 milliamps plus 0.4 milliamps is what? 10.4 milliamps. So my total coming around there is 10.4 milliamps. All right, so that's that one. C, 2.7 C. Now I have the voltage given over on the side, 30 volts, and I have the unknown voltage across here, which is 10K. But is it really unknown? No, it's the same as the voltage across the 30K, or the 30 volts. So it's the same as voltage across the 30K. So I have 30 volts here. I have 30 volts here. And I can find my current. It's what? 30 divided by 10, or 3 milliamps. And 30 divided by 30, or 1 milliamp. So I have 3 milliamps coming down here, 1 milliamp coming down here. What's the total here? 4 milliamps. So I know my current I is equal to 4 milliamps. Okay, D, that's C. D is, I have 10 volts, and I have 1 ohm. They try to trick you with flipping back and forth between K ohms and just ohms, but basically, if it's K ohms, you are in milliamps. If it's ohms, you're in amps. So now we're just in amps. This is 2 ohms. This is 3 ohms. And this is 4 ohms. So basically, we go 1, 2, 3, 4 ohms. So 10 volts divided by 1 ohm is 10 divided by 1 is 10 amps. 10 divided by 2 is 5 amps. 10 divided by 3 is 3.33 amps. 10 divided by 4 is 2.5 amps. So what's my total? I total is equal to 10 plus 5 plus 3.33 plus 2.5, or I get 20.83. And this is 20.83 amps. Okay, good, that's that one. Now 8, find the equivalent resistance of each of these guys. So now we have a starting point, and we're going to go down, we're going to track down the resistance, the R equivalent for each of these circuits. So here is 6K and 12K. That's easy. It's the reciprocal rule, or it's 1 over, it's this times this over this plus this. This is product over sum. Either way, it's a parallel. We recognize this as parallel because it can go either way. It can go this way, it can go this way. So this is parallel. Use the parallel rule. So it's 12 times 6 over 12 plus 6, which is what? Is the answer going to be greater or less than 6K? It's going to be less than, right? And it's significantly less than because this is close to this. So basically, it doesn't drop to 3, but it drops to something kind of close. So that's A. B, we have 9 and 3. Again, parallel. 3K and 9K. All right, okay, so we start here, we go down here, or we could go down here, so that makes it a parallel. If they're parallel, you can kind of see it, and use the parallel rule, which is 3 times 9 over 3 plus 9. That's product over sum, or you could use the reciprocal rule, but product over sum, if you just have 2, it's 27 divided by 12. It's 2.25, which is a little bit less than the 3, which is what we're looking for. So this is 2.25 k ohms. C, this is 2.8 C, is 100 and 300. Again, parallel rule, because they're in parallel. It's product over sum, 300 or 100 times 300 over 100 plus 300. And again, it drops to a little bit less than 100, or that's equal to 75 ohms. D is the same problem we had before, where we go from right to left instead of left to right. But I can redraw that, make it just the same, which is 1K in parallel with 2K. So my answer is what? Product over sum, 2K times 1K over 3K. So it's what? It's 667 ohms. D, or E, I have a 1K, I have a 2K, I have a 3K, and I have a 4K. So, how you do this one? Reciprocal rule. 1 over 1K plus 1 over 2K plus 1 over 3K plus 1 over 4K. Now, is the number going to be greater or less than 1K? It's going to be less than 1K, but not a lot. So 1 divided by 1,000 equals plus 1 divided by 2,000 equals plus 1 divided by 3,000 equals plus 1 divided by 4,000 equals reciprocal 480, which is, that's about right. You can see that it's going to be something less, but just practice this. 1 over 1K plus 1 over 2K plus 1 over 3K plus 1 over 4K. So it's 1 divided by 1K plus 1 divided by 2K plus 1 divided by 3,000 plus 1 divided by 4,000. And then the last thing you do is do the reciprocal of the 1 over X rule, and you find that you get a 480. So that gives you some practice with using the reciprocal rule. So product over sum, reciprocal. Can you do this with product over sum? Sure, you can combine these two, and then that with this, and that gives you the third one, and the final would be that sum over this would give you the fourth one. That's the Pac-Man approach, and you can do that if you want to. Munch it a little bit at a time, but usually you want to do it all at once. This is the all at once approach, which is what I prefer to do. Okay, so now we're going to find in these circuits all equivalent resistances. So this is 2.9 A. So I have a 15, I have a 50, and I have a 50. Now I am a little bit more observant here because this is in this you want to combine these two first and combine that with that. So basically we redraw. So leave the 15 alone, and the 50 and the 50 become a 25. This redraw becomes a what? 15 plus 25 is 40 ohms. So that if you just combine it down to one resistor, it's 40 ohms. Okay, so that would be A. B would be 1K, and then 4K, and then 3K and 1K. So here we combine the 3K and the 1K. That becomes 4K. So this, you can redraw that and say, okay, I have 4K here, and I have 4K over here. 4K, 4K, and 1K. Now I redraw again, and I have 1K up here, and I have 2K over here. And then I can redraw again if I want to, but I can see this is equal to 3K. So you crunch it down, combine these two, then you work that with this, and then you do that, and do this, and you keep doing it until you get it down to 1. That's B. C. All right, so C is no different. You start with, and I'm going to show you how to do this a little differently. Do it like goalposts if you can. Redraw it a little bit differently. Makes a lot more sense. 2K, 4K. Then over here you have 4K and 2K. So you combine these two and you get a 6K. You combine these two and you get a 6K. Now you've got two 6Ks in parallel. 6K parallel with 6K. Remember, if they're equal, you can do them in half, and exactly what you have. You have a 3K. So all this mess over here is equal to a 3K resistor. That's all it is. And then D, I'm trying to trick you by putting the terminal on the other side, but we can redraw it. 12.5K. And then what? A 10 and a 30 in parallel. So what is a 10K and a 30K in parallel? Okay, it's the product over sum, right? 10 times 30 equals divided by 40 equals what? 7.5. So these two are equal to, I got the 12.5 over here, and I got a 7.5 down here. Now what is this? This is in series. So I add the 12.5 to the 7.5, and I get what? 20K. So the one resistance for this is equal to 20K. All right, now the last one is a little bit more harsh because it asks you to do what we commonly call the accordion act, which basically means you crunch it all down and then you bring it back and then you find all the voltages and all the currents. And that would be the last step in this kind of a problem, where you would actually be asked to get all the currents, all the voltages in one of these problems. So this would be 2.10. This is the last part of this chapter, and we're going to work more problems than just these, but let's work these first. So if I put 10 volts across there, an A, I have 10 volts right there, okay? And I go 15K. Now, what are they asking for? All the voltage, all the currents, right? All right, so first of all, you have to simplify. When they ask you for everything, you have to do the accordion move, which means you crunch it all down, and then you bring it back. So basically 10 volts, 15K, 50K. So basically what you have to do is redraw. 10 volts, 15K, and 25K. So what's the current flowing around there? Well, these are in series, right? So 25 and 15 is 40K. So it's 10 volts divided by 40K. What is that? 10 divided by 40 is 0.25 milliamps. So now I know my current going through here, 0.25 milliamps. Okay, so now I know that, and I know the current. I know the resistance, so I can find the voltage. 0.15 times 0.25 is equal to what? So my voltage across the 15K is 3.75 volts. So if I start at 10, I go down 3.75. What is left? Well, the voltage across both of these is equal to what? 10 divided 10 minus 3.75. What is that? 6.25 volts, right? So the voltage across each of those 50K is 6.25 volts. So the voltage here and the voltage here is 6.25 volts. So what is my current? I of the 50K, each of them. It's 6.25 divided by 50K. What is that? 0.125, right? It's equally split, which is what you would expect. If these were equal and this was 0.25, each of these would be 0.125 milliamps. So now I know my voltages and my currents through each of these devices. So I could say I 15K, V 15K, I 50K, V 50K, and I can find all these values. 0.25 milliamps, 3.75 volts, 0.125 milliamps, 6.25 volts. And I got it. And this is for the either the left one or the right one, doesn't really matter. Okay, you see how this game is played? You crunch it down and then you basically solve that problem and you bring it back. Alright, so let's do that for next one. Let's do the next one. The same thing on the next one, which is 10 volts. So this would be 10 2.10 B. So I do 10 volts and I do 1K and then I do 4K and I do 3K and 1K. So remember, these add up to 4K, right? I can just put a little notification right there that that's 4K. So then this and this is 2K. So basically I have a circuit with 10 volts. And I have 1K up here and 2K over here, which gives me a current of 10 divided by 3K, which is what? 3.33 milliamps, right? All right, so that gives me my current. Now that I know my current, I know my voltage drop across the 1K, which is 3.33 volts. And now I know my voltage drop across the 4K, which is 6.67 volts. But I don't know what the voltage drop is across the 3 and the 1. Okay? But I do know that the voltage across the 3 and the 1 has to add up to 6.67. So here I have a little or simpler circuit. So I can find my current through this guy, which is what? 6.67 divided by 4, or 1.16, excuse me, 1.667 milliamps. That's the current right there coming down. Now, I don't know the voltage across these guys yet, but I know that some of the voltage across these guys is 6.67 volts. So now I can look and see what the current is through here. So I have, it would just be like I had a 6.67 voltage supply. And you say, can you do this? Yes, you can. I know the voltage across here. So I do know that I have a 3K and a 1K. And I can say, what is my current through there? Well, it's the same as the voltage across here. It's 1.67 milliamps. It's the same equation. So now I know my current through there. Now I can find my voltage. It's 5. And this is 1.67 volts. So now I know all my voltages, all my currents through this whole circuit. I know that this current up here is 3.33 milliamps, 3.33 volts. It equally splits 3.33 into 1.67, 1.67. The voltage across here is 5. The voltage across here is 1.67. Voltage across here is 6.67. 1.67 milliamps here, 1.67 milliamps here. I'm done. It's all taken care of. It's all good. That's B. All right, moving on. C is equal to, I'm going to redraw it the same way I did it before, which is a lot easier. None of that diamond stuff, if you can help it. So I have a 2K and a 4K, and I have 10 volts here, right? And I have a 4K and a 2K right here. So basically this is 6K and this is 6K. So if I wanted to find my I, 10 volts, my I would be what? What resistor would that be? It would be 3K, right? So it would be 10 volts divided by 3K, which is equal to 3.33 milliamps. Again, so what's steaming down here is, well, it's split. Some of it goes this way and some of it goes that way, but where it starts, right up here, where it starts, it's this. It's 3.33 milliamps. And you can see that it splits exactly equally, but I don't want to assume that because I'm a skeptic. So basically, now I can say 10 volts, 6K. This is what? I want to know my current right here. So it's 10 volts divided by 6K, or 1.67 milliamps. And it's 10 volts divided by 6K here, it's 1.67, which adds up to 3.33 or 3.34. So basically now I know my current and my voltages split like this. This is a third, this is 2/3, so this would be 3.33 volts, 6.67 volts, 6.77 volts, 3.33 volts. I'm done. And 2.10 D. So I start as if I were starting from the right or from the left instead of the right. I've got 12.5, and I come down. I go across 10K and down 30K, and then I bring them back together. So these combine to a 7.5K. And then I get to 12 plus 12.5K, so I have one resistor, 10 volts, of what? 20K, right? So what would make my current flowing through here? 20K divided by 10 volts is 0.5 milliamps. So my current here is 0.5 milliamps. Now here is my voltage, 12.5 milliamps times 0.5, or 6.25. So my voltage across here is 6.25 volts. If it's 6.25 volts across there, what's left? Well, the voltage across here and the voltage across here have to equal 3.75. So now I can find my currents. 3.75 divided by 30 is equal to 0.125 milliamps. What is 3.75 divided by 10K? 0.375, right? Milliamps. So I have 0.5 milliamps coming down to this point. I have 0.375 going that way. I have 0.125 going this way, and they add together. So 0.5 does equal 0.375 plus 0.125, which is a check on the whole thing. So now I've broken that problem down and crunched it down, and it works. So that should give you some good starting points to work on these crunch problems with what we call the accordion problems, where you crunch them down and you bring them back. Take care and have a good day.